Good afternoon. So we're going to make a start on a new chapter today. If you want to turn to chapter 5, please. Okay. So chapter 5 is not going to be easy. Let's get out of the way. So chapter 4 was a bit fun. We did lots of examples. It was about using the steam table. It wasn't, we didn't have a lot of equations, formulas, derivations. Chapter 5 isn't like that. Chapter 5, unfortunately, especially this session, has a lot of equations. So I need you to be patient, and I need you to focus. What's the good news? Well, the good news is, during the next lecture on Thursday, in fact, we're going to make a start on some very interesting devices, some very common devices that we have in engineering: turbines, compressors, nozzles, diffusers, pumps, etc. So we really start looking at these equations and how we apply our thermodynamic equations to these real devices. Before we start, are there any questions from last session? No? We're all happy with the steam tables? Yeah? Okay. So, something about chapter 4 and 3 and before that was really that we started looking at what we call closed systems. You saw the examples that we had in the last chapter, especially the last chapter, when we were looking at, for example, a piston and a cylinder. We looked at a pressure vessel. In most of the situations, we had a closed system. The mass wasn't really changing in the problem. In reality, that's not the case, because in reality, you have a system. For example, just think about a compressor. In the form of the jet engine. You've got the flow coming in and it goes out. In the turbine, you have the same. Steam comes in and goes out. Therefore, they're not closed systems. Most of the engineering problems are open systems. Let's just do a quick review of the sort of equations that are applicable to the closed systems. And these are actually in 3 different versions, or 3 different forms, if you like. So these are for closed systems. For now, you can ignore this equation, this one. And the reason is because we did skip one section where we had the surface tension and things like that. That's where the tau sort of came from. Therefore, you can ignore that equation. But essentially, you've got 3 forms here. You've got the integrated form, which is normally the longest. Then you've got the differential form. And, you've got the differential form, which is normally actually quite short. And it's easy to remember. It's easier than the integral form. And you've got the rate form, which involves a time. Again, let's just remind ourselves that when we say rate form, we mean an equation or a situation where you care about the time. So time actually matters. If you have a steady situation, then the time really doesn't matter, because you have a constant flow rate, for example, or actually you're looking at a snapshot of time. Therefore, you're not looking at a rate or time playing an important role. So let's just look at each equation and each term. E was the internal energy, and it had 3 components: the intrinsic internal energy, the potential energy, and the kinetic energy. And on the right hand side of the equation, we had the heat and the work. The same story when it comes to the differential form or the rate form. The only difference in the rate form is that you're now dividing everything by dt, and you get these dots essentially, which signify that rate form of the heat and the work. Now, before looking at the open systems, we want to be looking at this diagram, which we have had this diagram in the past as well. It's the only, or it's the simplest form of diagram that you can start looking at what's the, what represents a simple system. Imagine that this is, as I mentioned, it could be a balloon, for example, and this could be a small opening within this balloon. If you had a pressurized balloon, for example, there, and then and some air is actually now moving out of this vessel or this container, let's just draw this n, which is the normal vector to the direction. If you're wondering why we are concerned about this n, is because if you think about this opening, which is just a circular type of opening, you could have velocity in different directions, right? But what you're concerned about is the actual direction normal to the opening. So if this is a surface area, what I care about is actually the flow in this direction, the velocity exactly in the perpendicular direction to the opening. So that n there represents that. Omega is the control volume, and gamma is really your boundary. And you could have a number of boundaries in here. If you want to look at, and of course this is dA, is the elemental area. If you want to, for example, write down an equation for the elemental volume of material exiting at dA. If you want to sort of find out what is the amount of material, whether that is, could be air, could be fluid, what is that volume which is coming out of dA at any given time, that is given by this equation. You see V and N in bold because these are vectors, and actually V dot product N, that essentially represents your velocity, but the velocity which is perpendicular to the opening. Then you've got dA, which is the cross-section area, and of course you've got dt, which represents the amount of time that it takes. So if you want to, for example, measure the amount of volume coming out in 1 second, then dt is 1. If that's for 10 seconds, then obviously dt, for example, would be over 10 seconds. If you do the unit analysis of each of these parameters, then it actually makes sense, and you can find out that this, by doing dimensional analysis, you end up with, for example, here we're going to have meters per second multiplied by meters squared multiplied by s, and that gives you meter cubed, which means that is actually in a volume form. Now, if I want to actually measure the elemental mass exiting this dA, then this would be the equation. The difference, I've just multiplied that by rho. Why? Because then, if I multiply this by rho, which is kilogram per meter cubed, then essentially that unit would change to kilogram. And therefore that would give you the amount of mass which is coming out of dA over a certain amount of time. And I'm doing it step by step because then that allows us to derive this equation, which is the main one here. The next term which I'm looking at is this one. What's the difference now? I've added, or I've multiplied that equation by E. And E here is the specific energy. So the capital E was the internal energy, and small e is the specific internal energy. And by doing that, that really represents the elemental energy exiting dA. So through this equation, I can measure how much energy is leaving this container at a certain amount of time through dA. If you compare this equation to this equation here, the right-hand side is the same. The left-hand side, we've got one extra element, which is one extra term, which is this one. And in fact, the difference between the open systems and the closed systems when it comes to the application of the energy equation is this extra term. And that extra term is a bit which we're going to do some more analysis to understand exactly what it signifies. Again, let's just remind ourselves that the E has three components: intrinsic internal energy, kinetic energy, potential energy. So let's be clear on that. And the mass flow rate, dm, is really rho vn dA. And it's the same, if I told you what is the mass flow rate, the normal equation that you would say is rho VA, V representing the velocity, right? We've used that a lot in different situations. And if you think about that, then because V in here, if you're interested in the perpendicular vector of the velocity, then that would give us dm. And these two, when they're multiplied by each other, that's what that extra term, which would account for the change coming in and going out of your control system. In fact, one of the assumptions, it's not an assumption, it's actually, in a lot of situations, the energy within the control volume, or the omega, is 0, and therefore that term disappears. But that term, actually, in most cases, that term is non-zero, and this is actually why this is so important. Let's now start looking at further analysis on the energy equation. So as I mentioned, if the change within the control volume is 0, then your energy equation is simplified to this. And this is what we know as the steady flow energy equation. Applications: boilers, heat, aircraft engines, ice engines, heat exchangers, compressors. We're going to be looking at 6 examples in this, not in this lecture on Thursday, but in this chapter. In fact, we're going to be looking at 5 because we're going to skip the heat exchangers, but there are 6 examples included in this chapter, and they all use the steady flow energy equation. So it's actually very important. Now, we want to look at, we're going to actually expand the discussion on the energy equation, and we're going to give you an alternative form of this equation by using the concept of enthalpy, which we've used in the past. And this is a bit which might get a bit tricky. So again, pay close attention. In the first year in fluid mechanics, you remember that when we wanted to derive an equation, we normally start with a transport equation. For any scalar, for any property, you can define a transport equation. And that transport equation would allow you to define how that particular scalar or quantity would actually change in different situations. In here, what I'm doing now, I'm trying to look at the transport equation for mass, actually. In general, if you are defining a transport equation for any quantity, you've got 2 parts. Part 1 and part 2. Part 1 is looking at the change of that quantity, or the generation or destruction of that quantity within your control volume. And if you think about this, it shows that it's the rate of change of that quantity, which is m, within your control volume, which is omega, and that would account for what is the generation of that quantity within the control volume. The second term would account for in and out, or the sort of the net flux of that quantity within the control volume. It's difficult to give you an example. I normally use the lecture room as a control volume, and I use that as a classical example. In this case, it's a bit more difficult because when it comes to the generation of that quantity, which in this case is the number of people in this room, it's actually quite difficult to define that. But for now, let's just, if you want to, I'll try to make this clear now. If you want to have a measure of the number of people in this room at any given time, what are the parameters that you will take into account? Of course, if this is a busy room and people are coming in and going out all the time, of course you have to measure that. You have to count the number of people that are coming in within 1 minute, for example, and the number of people are going out within that 1 minute as well. 1 minute as well. That difference would be coming into this term. You also have to take into account the number of students or people who are already in the room, and if that number of people are even multiplying on its own within the room, for example, there's a generation of people, which is that's the weird bit, but if there are people being generated within this room, which could be actually for any scalar, if it's temperature or heat, obviously for people that would be a lot more complicated, but when it comes to other physical properties, then actually that could be possible, and you need to be aware of that in order to find out what is that quantity within the control volume. And that bit is that term to account for this. If you want to rewrite that, it's the mass flow rate within the control volume and the change in and out. And actually in simple terms, which this actually makes a lot more sense, is the mass flow rate exiting minus the mass flow rate coming in. That would give you the net, and that would be the generation or destruction within the control volume. And of course here suffix I and E stand for inlet and exit. Sometimes in textbooks you have in and out, I and O, but sometimes you have E and I. Doesn't really matter. And now I'm going to use the same concept and apply that to generic unsteady flow energy equation. And that U, whenever you have the unsteady one, it really just means that you're now including this term and you are including these dots, which is just the rate form, and which means you're taking into account the time. So what else? Going forward from here, this is the bit which I'm going to introduce that new extra, that new term, which includes the enthalpy as well. The most important thing, so far so good. You've got the energy within the control volume, then you've got the mass flow rate and the specific energy, and of course the reason why this is E, small e, and this is capital E is because of the difference in mass flow. Knowing that E is small e times m, and of course E dot is E times m dot. This is the part where we are going to introduce, or actually again remind ourselves about the work. So far we've seen two different forms of work. One was displacement, the other one was shaft work. Remember? WS, subscript S, that's shaft work. For example, where you have a propeller or turbine or whatever, a fan in the system. And we had WD, which was a displacement work as well, which is if you're moving a piston within a cylinder, that is displacement. So that W, which appears in this equation, actually has two components. Even though in the generic form, we don't show that, but in reality, you could have WS or you could have WD. And of course, if you're talking about the rate form, that's W dot, W dot S, and W dot D. We normally retain the WS in its original form. We keep that as it is. We're not that interested in the shaft work for now, but you've seen the sort of things that we do with the displacement work. And that is by using the fact that WD, and that is capital WD, we define that as PdV. Remember that? That was one of the main equations that we had in chapter 3, I think. And I could actually write this as PV dm. And what I've done, I've converted capital V into small v by multiplying it by m. Again, knowing that I could write v small v times m. I could also, if I want to write W dot D, on that basis, I could write this as PV v dm dot. Right? So I've divided both sides by dt. Now, what I want to do is I want to move this term, which by now you know this represents w dot d. I want to move this term to the left-hand side of the equation. And what I mean by left-hand side, I mean the left-hand side of this equation here. So if I do that, then you end up with, let's just write this on a piece of paper. So I'm going to write the equation from scratch. I've got E dot CV plus M dot E and EE minus M dot I EI. That was Q dot minus WS plus WD. And I said I want to move that to the left-hand side, but before doing that, let's just note that that is Q dot minus WS dot minus PVDM. Move to left-hand side, and that means that now I'm going to have E dot CV plus M dot EEE okay, so the reason why I've done this is because I'm interested in combining. So what I know, let's just write this one. E, as we know, that's the specific internal energy, has three components, and that is U plus half V squared plus GZ. And E plus PV, if I wanted to, for example, if I had PV, and if I wanted to combine PV with E, I would then have U plus PV plus half V squared plus GZ. And this is what we define as enthalpy H. And this is what I've done actually in going back to notes. Are you done with this page? Give you a few more seconds. Now, what you see here is that the E has now the superscript H, and this is the sort of the new term which we introduced, and what it really signifies is that EH has two components. It's actually E plus PV, and of course this is what we know as a conventional definition of E, the three components, and when you combine it with PV, then it gives you H plus half V squared GZ. Because UPV gives us a very useful parameter called H. So the question is, why do you do this? Why do you need to write your unsteady energy equation, unsteady flow energy equation in this form? It goes back to the same reason why we introduced enthalpy in the first place. It's because the internal energy, or U, intrinsic internal energy, U, isn't sufficient to represent the full potential of the flow to do some work. It's only when you combine that with PV that gives you a very useful concept. to sort of show the capacity of the flow to do some useful displacement work. And therefore, by doing and going through all those analyses, we have a new form of the unsteady flow energy equation, which replaces E with EH and changes the right-hand side from a normal W dot to W dot S. And I hope by now we appreciate the difference between this equation and this equation. And you know that this now has been converted to WS because the WD component has moved to the left-hand side in order to lead to the new term of EH as opposed to E in that equation. I think until we do some more examples, this all seems quite theoretical, but then when it comes to some examples, actually you'll appreciate why this form of this equation is actually a lot more useful. We could actually multiply all the terms by dt and even define a new or a sort of an alternative form of this equation, which means now I've got rid of the rate form. There's no time involved. Sorry. So there's no time involved now. And in case you're wondering why again we've gone back to delta, again for the same reason why we mentioned earlier, that mass is not a property. And therefore, similar to Q and W, because mass is not a property, we have to use the symbol delta when referring to this in this form. Now, if you want to do a quick dimensional analysis on the displacement work, so we define that as m dot PV, and if you start looking and putting the dimensions or the units for each of these components, then you end up with joules per second, which is essentially W watts, and as we know, work is measured in watts, and that's proof through dimensional analysis. Now we're going to be doing slightly more, I think 2 more pages on the on different forms of this equation. So bear with me. At this point you might be wondering, what is the physical significance of this displacement work? You've heard it, you've seen the symbol W dot S or WD, sorry, W dot D or WD, depending on how you look at it. But what is the physical meaning of the displacement work? This example here shows how this term is redefined. I mean, the term m.pv, which we know is a displacement work, how does it appear and what does it really signify? Look at the system, and this is a system where you could, for example, have a shaft representing Ws, that's the shaft work. You could have some heat going out. We don't care at this stage about that, but that represents that term here, and that represents that term here. Then here, if you actually zoom in this area, you'll see something like this. And in fact, this is even a more magnified version of that image. And I'm going to be looking at this. This area here, that gray square, that, for example, represents delta M inlets, or just delta M. And that movement, or that displacement, actually is your dV. The displacement work, so if you want to convert it into some physical meaning, it is as if you've got a piston and you want to move, or you want to displace that fluid here, and this, for example, could be a fluid. Imagine that you want to displace this part from outside and move it into the inside of the device. If you're trying to push something inside this device, you might have some resisting force. And the resisting force, in this case, is a pressure, which could be the internal pressure within the system. So that's the PI. And the amount of work that you need to push this inside the system is what we define as this term here, WD, which is delta M times PI, which is the resisting force or resisting pressure, times the displacement, which is V, and that's the sort of the displacement size and how much you've pushed this inside the system. So that is the sort of the physical meaning of displacement work. Some more equations and some more forms of the energy equation. Why do we do so much? Why do we have to deal with this equation so much? Is because this is one of the fundamental equations. It's like the momentum equation in fluid mechanics. Okay? It's so important. And therefore, we need to define lots of different forms that are out there. We're going to start with what we know as the unsteady flow energy equation, right? That's that. And of course, we've put the unit there as well. That's watts. If you want to ignore, if it comes to the steady state, then that term disappears, and therefore this represents the steady flow energy equation. So the only difference really just being that that term has disappeared, and because it is a steady, m dot E, m dot I, they are exactly the same. So you can get rid of that subscript for the mass flow rate. You could also divide all the terms by m dot, and that gives you specific values. And of course, the unit will change to joules per kilogram. You could define this equation in the form of differential form. And remember I said when it comes to differential form, it actually becomes quite simple, if you like. Because you don't, essentially the symbols become a lot easier, and therefore it's quicker to write. And what you end up with is you're going to have the change in enthalpy. You're going to have the change in the kinetic energy. The kinetic energy, that's the potential energy. And of course, the change in the Q and W. Being careful that, again, you've used delta. Something interesting actually here, this paragraph here is actually about the Bernoulli's equation. Now, this is the interesting part, because so far we've been talking about something completely different. We've been talking about the steady flow energy equation. We've been talking about work, displacement, shaft work, heat, enthalpy, things like that. If you make some assumptions, if I make an assumption that there's no shaft work, so there's no propeller, there's no turbine, there's no compressor involved in here, then we know that that term is going to disappear, delta WS. If you assume that we have adiabatic situation, which means there's no heat exchanges in the system, then you're going to have delta Q equal to 0. If you now also assume that this is isothermal and incompressible, if it's isothermal, then the change in the internal energy is going to be 0, if the flow is incompressible, then we know that the change in density is going to be 0. And that equation actually reduces to, first of all, the right-hand side will be equal to 0. The left-hand side, what you end up with, you've got dH, vdv, gdz from here. These are the non-zero terms. And this will be actually written as what you see here. Now, you might be wondering where this p rho comes from. Can you just, for a few seconds, can you think about how we get from dH to p over rho? Do you remember any equation that we've used in the past couple of weeks which would relate dH to du, and etc.? Do you remember the equation dH equals du plus p dv? Yeah, that's essentially the definition of H. Because we're saying that this is an isothermal problem, that means that disappears. And because we could write, and of course because this is incompressible, therefore the specific volume is not going to change, and that could be written as 1 over rho, because the specific volume is really the inverse of the density. And by doing that, essentially you're going to have dH is equal to p over rho. And if you put that in here, then you end up with a very familiar equation, what we have, what we know as the Bernoulli's equation. What this actually shows is that because they come from the same principles, these are essentially the mechanical energies form of the momentum equation. The momentum equation is the fundamental equation here. And by having the right assumptions, essentially by making these assumptions here, you've removed anything to do with the thermodynamic aspects of the momentum equation. And then you're left with the core of the momentum equation, which you see there. These are the terms that are included in the Bernoulli's equation. And this sort of very nicely links the fluid mechanics to the thermodynamics and shows that while they are two very different subjects, sometimes when it comes to the fundamental equations, they have a lot of similar roots. I'm just going to sort of give you a quick overview of what to expect in the next session on the lecture next week. And this is the part which I said actually it's going to have some real engineering applications. On Thursday, we're going to be looking at 5 or 6 examples. And these are essentially adiabatic machines. We call them adiabatic because we assume that there's no heat transfer. You all know by now. And the adiabatic machines that we're going to be dealing with are compressors and turbines, and plus pumps, if you like, because pumps are sort of similar to compressors. We just use compressors for gases and we use pumps for fluids. That's the only difference. But as far as the cycle and some of the equations are concerned, they're actually quite similar. We're going to be using, if you actually start looking at some of the pages further on, page 7, page 8, etc., we're going to be looking at these devices, and for each, we're going to be looking at different form of the energy equation, the steady flow energy equation. and we're going to see what they really mean and how we're going to be dealing with these equations. Because I know we've been through so many equations today, I don't want to again dive into lots of derivations and lots of equations, so I think I'm going to stop now and give you some extra time to rest. And if you have any questions from anything so far, please come and see me in the next 5-10 minutes. Otherwise, just go home and relax. Okay?